Welcome to Humber's Numbers. I'm Rose Humberstone. Today we're going to be looking at functions and graphs, the other graphs, and also combining functions as part of Mathematical Methods Area of Study 1. In this video, we'll be focusing on other graphs and combining different functions. We'll start by combining functions, then we'll look at other graphs, then we'll look at some important things to note when graphing, before concluding with some sample VCAA questions. Combining functions. We're going to look at three different things: hybrid functions, addition of ordinates, and composition of functions. Hybrid functions are also called piecewise functions. They have different rules for different parts of the domain. I've got an example here which shows that they may also be discontinuous. So we can see here that there are three parts to the graph. For values of x less than -1, we have this rule here. When x is between -1 and 2, we have this rule here. While if x is greater than 2, then we're going to have this rule here. So you can see that there are three different rules for different parts of the domain. Addition of ordinates is also a useful way that two functions can be combined. We can add or subtract two functions together by adding or subtracting their points. The resulting function is only defined when both functions are defined. This is really useful for graphing. For example, if we have the rule 1 over x plus x, then we can combine the 1 on x rule, given by this red line here and this red line here, and the y equals x line, given by this rule here. Then, for each x value, we can add the 2 points together. So, for example, when x is 2, we're going to add 2 and 0.5 to give us our point here of 2.5. Notice also that the graph of 1 over x is undefined when x equals 0. As a consequence, our final graph of 1 over x plus x is also undefined when x equals 0. Another way that functions can be combined is composition of functions. Two or more functions can be applied to give a new function. So, for example, the new function h is formed by applying the function f and then applying the function g. We write this as h of x is equal to g bracket f of x. We can think of it as taking our input value of x and giving it to the function machine of f. This gives us the output of f of x, which now becomes the input of our second function machine, g. This gives an output of g of f of x, where f of x was the input. And then that's our output. Now let's look at some key types of graphs. So there are a number of different types of graphs that you must be familiar with. Obviously polynomials, which have been considered in another video. Then we have power functions, square root, rectangular hyperbolas, exponentials, logarithms, and circular functions. This video will just give a very quick overview of these. So the rectangular hyperbola and the truncus, the basic graphs look as follows, and each of these can be transformed. Notice that the truncus is always positive since we're squaring the x. Then we can get some graphs with positive fractional powers. So to start with, we have y equals x to the half. Notice that that's undefined when x is negative, because we can't take the square root of a negative number and get a real number. Then we have y is equal to x. Then we have y is equal to x to the power of a third. Then y is equal to x to the power of 2/3. Now this point here deserves further attention. It's called a cusp, and you must always put the coordinates of the cusp on your graph. The other thing I would say is that you should notice that y equals x squared is the inverse of y equals x to the half. So that is if I was to draw my parabola, or at least half my parabola, you can see that that's a reflection. Similarly, we could do the same thing with our cubic. Next, we can also have graphs with negative fractional powers. We can have y equals x to the negative half, or y equals 1 over the square root of x. And again, x cannot be negative in this case because we can't take the square root of a negative number. Or y equals x to the negative 2/3, where x can be positive or negative. In both of these cases, x also can't be 0 because otherwise we'd be dividing by 0. The exponential and logarithm graphs are two graphs that you should be well familiar with. Notice that for our first graph, the exponential, I've graphed y equals e to the x, but the graph looks very similar for other bases. There's also one horizontal asymptote given as y equals 0. There's also one horizontal asymptote given as y equals 0. Some students mistakenly put in 2, which is clearly wrong. For the logarithm, I have y equals log base e of x. This graph has one vertical asymptote at x equals 0. One thing that you should note is that your VCAA exams don't write ln for log base e. As such, I'd advise you to avoid this. We also have circular functions, sine, cos, and tan. With our sine and cos graph, we should note that the period is 2 pi, while for tan, the period is pi. That is, the graphs are going to repeat every 2 pi or pi, respectively. The other thing that we can note is that the amplitude is 1 in both cases. For a tan graph, it doesn't make sense to talk about an amplitude. However, the tan graph does have something that the sine and the cos graph don't have, and that is the asymptotes. These should be indicated and labelled. The asymptotes occur whenever cos of the angle is equal to 0. Remember that tan of an angle is equal to sine of an angle divided by cos of the angle. So if cos of the angle is 0, then tan of the angle doesn't exist. Okay, so some things to note when graphing. Intercepts, stationary points, and intersection points should all be given as coordinates. Asymptotes should be given with their equations, and your graph should be done in one line, not as a series of many little lines. I would also recommend that you draw your graphs in pencil. That way, if they don't go well, you can always erase them and do them again. So let's move on to some sample VCAA questions to see how what we've learned can be applied. First, let's consider the 2008 Exam 1, Question 2. In this question, you are asked to sketch the graph of f, going from the reals not including negative 1, arrow r, of f of x equals 2 minus 4 over x plus 1. You're asked to label all axis intercepts and to label each asymptote with its equation. Okay, so the first thing to note is the type of graph that we have. So it's a rectangular hyperbola. These graphs have the basic shape that looks a bit like this. However, there is a negative sign in our rule, indicating that it's been reflected. Okay, so let's get sketchy. First off, we have an asymptote at y equals 2. So let's put that in. We also have one at x equals negative 1. Putting these in first gives us a bit of a guideline of where our graph should go. Next, we need to find our x-intercept and our y-intercept. Our x-intercept occurs when y equals 0. So we're going to be solving 0 equals 2 minus 4 over x plus 1, which is the same as 4 over x plus 1 equals 2. So 4 equals 2 lots of x plus 1. So 2 is equal to x plus 1. Therefore, x is equal to 1. So my x-intercept is occurring here at x equals 1. My y-intercept, which occurs when x equals 0, is going to be given as y is equal to 2 minus 4 over 0 plus 1, which is just 2 minus 4, which is negative 2. So that's occurring here. So now we can sketch our graph. When we're sketching a graph with asymptotes, we want our line to get closer and closer to the asymptote, but we also don't want it touching, and we don't want it looking like it's about to cross if it were to continue. Once we've got our graph, we then need to label our axis intercepts. So here we have 1, 0, and our y we have 0, negative 2. Okay, so just to double check, labelled our axis intercepts yes, and labelled each asymptote with its equation, check. Now this question was actually worth 4 marks, so quite a lot, given the whole exam is only worth 40. Only 57% of students got all 4 marks, and really there's not a lot to this question. Just make sure you take your time and label everything properly. The next question we're looking at is the 2015 Exam 2, Multiple Choice Question 1. Now this is a very straightforward question, and it's a good one just to get you started in the exam. So we've got a sine graph given as 2 sine of 3x minus 3, and we've been asked what the period and the range is of this function, respectively. Okay, so for a sine graph, the default period is 2 pi, and in our case, we have 2 pi divided by 3, since we have a 3 here in our equation. So the period is 2 pi and 3, which means that we can immediately discard D and E as options and also C. Okay, now let's work out the range. So the range usually is from negative 1 to 1. However, a couple of things have happened here. First, the amplitude has meant that the range has gone from negative 1 to 1 to negative 2 to 2. So it's stretched out. And then it's been shifted or translated down by 3. So now negative 5 is my minimum and 2 minus 3 is negative 1. So my range is negative 5 to negative 1, which means my answer is A. Now for that question, as I said, it's quite a straightforward question, and 95% of students got it correct. Next up, we have another circular function question. This one's from the 2011 Exam 2 Multiple Choice Question 15. Here we've been given part of a graph, and we're asked to find what the rule of the graph is. Well, the first thing to note is that it's been shifted across, and it's also been shifted up, and the amplitude has changed. So let's start by looking at the amplitude. The current range is going from negative 1 to 3. What that means is that that's a total of 4, so the amplitude must be 2. What does that tell us? Well, it tells us that we can immediately eliminate C and D as options, since they have an amplitude of 4 and of 3 respectively. Next up, we can also see that it's been shifted up by 1. How do we know this? Well, usually the range is negative 1 to 1. An amplitude of 2 would mean it would go from negative 2 to 2. But instead, our range is negative 1 to 3. So it's been shifted up by 1. Now, unfortunately, we've still got 2 options here left, A and B. But we can cross out C, since that goes down by 1. All right, next we could look at the period. For the period, we need to look at what the distance is between those two peaks. So 2 pi over 3 minus pi on 6. Well, that's pi on 2. So therefore, I need pi on 2 to equal 2 pi over n. What is n then? Well, therefore, n must equal 4. So looking at my options here, my answer must be B, since the period for A is 1. So I can cross out A. So therefore, my answer is B. Now, lastly, I could check to see what's going on with the translation. So we have a cos graph here and a translation of pi on 6. So indeed, B is the correct answer. Now, only 67% of students got that one correct. The next question comes from the 2013 Exam 2, Multiple Choice Question 5. Here we have two functions, f, which has a domain of negative infinity to 1, and the rule is 2 log e 1 minus x, and g, which has a domain of negative 1 infinity, and the rule is 3 square root of x plus 1. And we've been asked what the maximal domain is of the function f plus g. Now remember, when we're adding two functions together, it's only defined if both functions are defined. So let's have a little think about what's going on. If this is my number line here, then f is defined from negative infinity up to 1. And 1 is not included. So this is what f is defined for. In contrast, g is defined from negative 1 to infinity, but negative 1 is included. So the part of the domain that is defined for both is from negative 1 inclusive up to 1 not inclusive. So negative 1 up to 1 round bracket, which is answer A. 75% of students got that correct. Now, it's not a terribly difficult question. All it's doing is testing. Do you understand that adding two functions together means that the domain has to be defined for each of them? The last question we're going to look at today is the 2007 Exam 2 Multiple Choice Question 22. Now, this is a pretty standard type of question. In this question, we're given the graph of f and the graph of g, and we've been asked which of these graphs best represents the graph of f of g of x, that is a composite function. Now, the way to think about this is to think about what would happen if x was negative, 0, or positive. So let's start with x being 0. Well, if x is 0, then g of x would be 0 here. And f of g of x would also be 0. So therefore, my graph must go through 0. And we can see that means D is not an option. What if x is positive? Well, if x is positive, g of x will be negative. If I take a negative value and I give it to f of x, what happens? Well, it's positive, because a negative value becomes positive. Okay, so let's see which of our graphs this matches. Well, when x is positive, I must have a positive. Well, here it's positive, but it goes back to 0. So I've got an issue here. Here we also have an issue. It's negative. So I can cross out both A and B. E, that looks pretty good. It's positive. And C, well, it's negative and negative. So I can cross out C. So it looks like my answer is E. Let's just double check what happens if x is negative. Well, if x is negative, g of x is negative here. And f of a negative number is also going to be positive. So when x is negative, f of g of x should be positive, which is what we have here. So therefore, my answer is E. Now, only 37% of students got that correct. It's a pretty straightforward question. One just has to be methodical about it. Well, that's the end of today's video. If you've got a question, you can leave a comment, or you might want to go back and watch the relevant section. Our next video will continue to look at area of study 1 by focusing on transformations.